today we're going to learn something. You spent the last week basically learning how to integrate over all sorts of different shapes. You've got a quiz on that tomorrow, right? You did a point charge, then you did multiple point charges, then you did a continuous line of charge where you had to integrate, then you did rings and arcs, then you did sheets and planes and disks, and your brain is probably sick of integrating right now. So what I'm about to show you is something where we can get rid of all of that math and make life super, super easy. All right? So this is a trick. It's called Gauss's law. But before we talk about Gauss's law, I'm going to just point out a few pictures to you. First of all, if you had an infinite plane of charge like that, which way would the field lines point?
Vertically. Perpendicular to the plane.
Perpendicular. Would they spread?
No.
No, they would not spread. What about an infinite cylinder? Which way would the field lines point?
Perpendicular in all the normal. It's all the.
Yeah, all the normal lines. It's out from the cylinder in every direction, right? And then if you had a sphere, it would be out from the center of the sphere in all directions, right? Perpendicular to the surface, keep on going. Now, so these are the three basic shapes we're going to deal with in AP Physics C. More complex versions of these shapes. What if you had two infinite planes, one on top of the other? Which way would the field point?
Positive and negative.
Yeah. All right, coaxial cylinders. Well, we've got one cylinder inside another cylinder. Yeah, one would be pointing straight in and hit the other one. And then concentric. What? Do you guys know the difference between coaxial and concentric?
Concentric is inside. They share the same center.
Share the same center. And coaxial means share the same axis. All right? So you use the word coaxial to describe cylinders and concentric to describe spheres. Got it?
Yep.
All right. So, here we go. What if I drew... Actually, no, let's go back to this idea of a sphere. Can you see that if I were to draw field lines coming out of a sphere, the field lines would never curve?
Yes.
They would go straight. What about for an infinite cylinder? Would the field lines ever curve?
For an infinite cylinder?
Infinite cylinder, no, right? What about an infinite plane? They would never curve. So that means that if I had another sphere outside of this sphere, the first sphere, if I had another sphere out here, the field lines from the first sphere would impact the second sphere perpendicularly. Wouldn't you agree? Well, that's kind of a symmetry. All right? When I talk symmetry, when I'm talking electric fields, I'm talking if you had a bigger shape of this, same shape, bigger size, just scaled up, and all the field lines pretty much would pass through it perpendicularly, we say that shape has Gaussian symmetry. Now, there are only certain shapes that are like this. Sphere is one, an infinite cylinder is another one, an infinite plane is another one. Do you see what I'm talking about, Dino?
Oh my gosh.
All right, so if I had a bigger sphere outside this first sphere, all the field lines would hit the bigger sphere perpendicularly. Right? If I had a one, yeah, okay, good, right? We say that a sphere has a certain symmetry that allows any field lines that project from it to always go the same direction, no matter how big the sphere is. Same thing with a cylinder. If you had a bigger cylinder, the field lines would still be behaving the same way. Agree?
Yeah.
And if we had two planes, one plane stacked on top of the next plane, the field lines would always be behaving the same way. There wouldn't be any curving to the field lines. Is this true for every shape? Let's say I had a cube that was charged up. Would the field lines coming from a cube always be straight?
What about the corners? Yeah.
Would they always be straight? So here we go. So cube. So I'm going to draw a cube. Here's a cube. All right. The field lines are coming up, going sideways, going down from the bottom, going left from the left side, coming out from the front side, going back from the back side, right? However, doesn't that imply if they didn't bend, there wouldn't be any field right here ever?
Yeah.
Is that true? So what has to happen?
There's got to be some kind of bend.
There's got to be bending. So in fact, the field lines bend up and out, like that. Does that make sense?
Yeah.
You what?
All right.
There and not electricity.
So we say the cube doesn't have symmetry like a sphere has symmetry, because the field lines bend, which if you put a bigger cube outside of the first cube, the field would be different. See how that works? So cube doesn't work. What about a smiley face? Of course not. Or a Mobius strip?
One-sided paper.
No, of course not. All right, only certain shapes have this symmetry, and these are the shapes that we are going to use in class. We're going to leverage this symmetry idea to make problem solving really frickin' easy.
Are there any other shapes that have this?
Oh, that's an interesting question. Are there?
You want just to know the answer?
Can you prove it one way or another?
Well, I assume they exist.
Or are these three shapes special?
No matter how many sides, between them, then I have sides. Which can be a circle. Or a sphere, I should say. Well, the cylinder and the sphere are both like circular based.
No, they're not.
I was just kidding.
The sphere is point-based.
Yeah.
It's got the same symmetry as an individual point.
And the cylinder.
The cylinder is line-based, a one-dimensional object. So the sphere has the symmetry of a zero-dimensional object. The cylinder has the symmetry of a one-dimensional object, and the plane has the symmetry of the most basic two-dimensional object.
Most basic 3-dimensional. Yeah, what's the symmetry of 3?
Hold on. So, yeah, 0 dimensions for this point, right? 1 dimension for a line, 2 dimensions for a plate. Those are the 3 options for 3-dimensional space. In order to describe something that was a 3-dimensional object that would fit this rule, you'd have to be working in 4-dimensional space, right? Got it? So,
How do 4-dimensional people look
like you. Yeah, three space and 1 time. That's 4 dimensions.
So,
Absolutely.
So what's the 5th dimension?
What do you mean?
why can't we find like a 3-dimensional?
Because we need another space dimension. Right. We've got 3 space and 1 time dimension that we're in right now. Yeah, what would we look like if we didn't have a time dimension?
We'd be frozen in place.
It'd be frozen and nothing would ever happen.
Oh, wow.
Yeah.
Dang, I would look this dude forever.
Well, the concept of forever wouldn't exist.
There'd
Right?
be no time. You'd
Yeah.
just be a place.
There'd be no such thing as change.
So you just exist.
Yes.
You wouldn't be born.
No.
People would just exist.
Yes. If there were people. Yeah, it'd be like a painting. Except a painting that never decayed. Right? Nothing would happen. It'd be a very boring universe. All right. Anyway, moving on.
And so what?
Yeah, this is all getting recorded. All right, moving on. Next topic. Do you guys ever hear what the flux?
Yeah.
Yeah, we know what that is. What's flux? What is it? That's a question.
It's the chain.
Yeah.
No.
Whoa. Yeah, what is flux? Do you guys remember this?
Because it's when you have a magnet and you put a field so you get a
Yeah, the magnet and the thingy. Last year you talked about only one kind of flux. It was magnetic flux. But the basic idea was this. You have a ring,
Yes.
right? This ring is sitting in a field. Here's my field. Here's my field. And these field lines, right? And a certain amount of the field lines actually go through this ring, right?
Yeah.
Well, the ones that do are called the flux. And the ones that don't are not. That make sense?
Yeah.
That's what flux is. All right. So how do you capture more field lines?
Larger.
A bigger ring will capture more field lines. What if you want more total flow through? Well, you got a couple options. You can either pump more field through, right?
Yeah.
We have a stronger field. Or you can use a larger ring. Or you can actually change the angle of the ring. Because how much flux will happen if the ring's like this? That'll be none. It won't capture any because it's kind of sideways. Does that make sense? So flux is the amount of field lines going through a given area.
Okay.
Well, yeah. Or through a given shape. And if that shape is rotated sideways from the field, then the flux is 0. By the way, what if you rotated 180 degrees? The flux will be negative. So if I have it this way, if it's going through this way, it'll be positive flux. And if it's going through the other way, we call that, negative flux.
Is there any change in like the properties?
What's that?
Is there any change like the properties?
The
Like,
properties.
Can you tell like which if you're just given something like that, can you tell like this is obviously negative flux in turn?
No, a flux is just a purely abstract concept. It doesn't have any physical properties. Yeah.
How do you know which side's positive or side's negative?
You have to define the positive side and the negative side. All right. Now, that's a good question, though. All right, so last year we talked about magnetic flux, phi B, which was the amount of magnetic field that passed through an area. This year we will first introduce electric flux, which is, guess what? Electric field through an area. And how do you get flux? Well, you have an electric field, E, right? You got E. Then you got an area to go through, A. And then what's this cosine theta thing?
The angle to which.
Yeah. So like if you go through like this, what's the angle?
90.
No, that's 0.
Oh.
Right? You go through like
Cosine
this
of 1.
because maximum is
Was cosine of 0?
right. So this would be like a 45.
Yeah.
And then this 90 degrees is when you have no flux.
Right.
All right? And then 135 degrees you have negative flux. 180 degrees you have maximum negative flux. Does that make sense? So it's kind of weird. We actually define the angle by, are you guys familiar with this? We do a normal vector from this plane. And then, so I'm using one stick as like the normal vector from the plane from my ring. And then the other stick is like the direction of the field. Yeah, and so we do the angle between the field and the normal vector. So this is like 30 degrees right now. Does that make sense? Yeah, and Macy was right. It's a dot product, so it's field dot dA. Yes. Yes. Now the total flux, little piece of flux would be delta phi, or d phi equals E dot dA. Well, if you want to figure out the total flux for a whole area, it would be integral of E dot dA if you've got this crazy area thing. All right, let's actually go to the packet real fast, and we're going to actually do some examples. So, we talked about the total flux is, you gotta add up all the surfaces and figure out what the flux is through all the surfaces to get the total flux, right? Now, if you had a continuous shape, that would mean you're doing an integral. Let me switch back over to the Apple TV here. So, total flux, if you do it as an integral, would be add up the integrate over all the area. And you know, if it's a cylinder, you'd have to actually do a piecewise integral. Do you guys know what I mean when I say piecewise integral?
Yeah.
This piece, and then the top piece, and the bottom piece, and then the side piece. All right, so that would be horribly complicated to do. Graphically, here's what we're looking at. If you had a flat plane, like a loop of wire, I think they showed you last year, Macy, the electric field would be here, the area would be here, and the angle would be the angle in between the normal line and the electric field. But if you had a curved shape, think about that. Let's say you had a curve, like a cup, shaped like this, right? And you had field coming into it. What would be the angle right at this point? 90 degrees. Actually, no, that would be 0 degrees, right?
Yeah.
What would the angle up here be?
90.
90 degrees. And it'd be changed from 90 degrees to 0 degrees. So you would have to integrate over all of those little E dot dAs, which would be a horrible thing to do. It'd be a horrible multivariable thing to do. But this isn't a multivariable class. But what we say is the total flux through an area is the integral of E dot dA for every little piece of area on this cup shape. Does that make sense? Mm-hmm. All right, fine. I'm not going to move on. Let's say you had a balloon. Say you had a balloon. The balloon is shaped like a balloon. Shaped like that. And you had a point charge right here. As a positive point charge, right? Now, which way does the field go from a positive charge, Macy? Ow, darn it. Out, it goes out, right. It goes out from a positive charge. And they're equally in all directions, right? So if some would go like that, like that, like that. So what I want to know is this charge is going to create a field that's going to go through the balloon, right? Yes. What I want to know is the total flux going through the balloon positive, or is it negative?
Or is it 0?
Going more out.
Wait, let's ask this again. Here's the point charge, here's the balloon. Is it a positive flux or negative? Is there a net inward or a net outward?
No, because outside, it's a singularity outside a closed curve, and then that
It's
flow is 0.
zero because
Yes.
it's like that is strong.
Zero.
And it's like
What's singularity? Where is it?
yeah.
Singularity is the
Somebody who's not in multivariable.
It's positive.
It's
Zero.
0. You.
Positive.
Why do you say positive?
Because the top and the bottom.
Wait, hold on. Listen to my logic. Isn't the field closer to the close side of the balloon? And therefore, isn't the field on the close side of the balloon stronger than the field on the far side of the balloon?
But there's more field area on the far side.
Doesn't matter.
We're going in.
Wait, Dino, wouldn't you agree with that?
Yeah.
So isn't there more, therefore, the effect of the field on the close side of the balloon stronger than the effect of the field on the far side of the balloon?
Yeah.
Because it's a stronger field, right? Wait, do you have a counterpoint to that? What's your counterpoint?
There's greater spread on the other side.
Wait, what?
It spreads out farther on the other side, so there's a greater area outside affected by it. So even if it's a lower strength field, it's like the gravity thing.
Ah, right. So Solom's argument is, yes, the close side has a stronger field, but it's over a smaller area, right? And we know flux is actually field times area. So the far side of the balloon has a bigger area. Therefore, even though the field is weaker, what do you say?
They have to, yes, it cancels out to be zero.
It's offset, and you're exactly right. It exactly offsets. The strong field on the front side is on a small area. The weak field on the back side is over a big area. So the net flux is what? Zero. Do you understand? Shrina, do you understand the picture? All right, so there it is. So this is the big example. And having so many multivariable people in here makes it annoying. Right, annoying. You're like, well, we know what flux is. Yeah, the answer is zero. All right, and here's the other way to think about that.
Mr. Bruce is like, is it cheating if we figure it out that way?
Oh, we're going to get there in just a second. All right, so here's the quick and dirty answer to this balloon question. Any field line that crosses into the balloon has to do what? Exit out of the balloon. So any field line, if you've got 10 field lines coming in, how many have to come out? 10. And therefore the net flux has to be zero. Yes.
What if there's like an insulator like on the inside of the balloon, so it only like
It doesn't matter. It doesn't matter. You can't just suddenly destroy field. Right. All right, so let's keep going. This brings us to this super powerful tool called Gauss's law. We just derived Gauss's law, by the way. And Gauss's law is, if a field line passes into and out of a balloon, its contribution to the total flux is zero, right? If you have a closed surface, the only thing that can contribute to the flux is any charges that are inside of the surface, inside of the balloon.
Hey, wasn't that on our lit sheet?
Yeah.
All right?
That's what I thought.
Only things that are contained in the balloon can contribute to the net field. So, what if I put a charge inside that balloon? A positive charge inside that balloon. What would the flux be?
It would be overall negative.
What?
It would be overall negative, positive.
If I put a positive charge inside the balloon, the field would be positive. If I put a negative charge inside the balloon, the flux would be negative. Got it? All right. So, equation-wise, what this looks like is the total flux is equal to, the total flux through is the integral, but there's this little circle. What's that little circle mean? It means, actually, I'm drawing this incorrectly. Technically, it should be a double integral sign. Two integrals with a circle.
Here we go.
Yeah, two integrals with a circle. That means a closed loop surface integral of E dot dA. Basically, it means I have a balloon. And the total flux through the balloon is the charge enclosed divided by epsilon naught. Hey, there's epsilon naught. Notice the lack of K.
Because it's not 4.
It means the flux is equal to the charge divided by epsilon naught. The flux through the balloon is equal to the charge enclosed divided by epsilon naught.
So then, the permittivity constant is dependent on.
Is a constant. Is a fundamental constant of the universe, like big G. It doesn't depend on anything. All right. So here's how it gets useful. I'm going to go through, and we are going to prove this super, super fast. You ready? Here we go. Actually, do we have time for this?
3 minutes.
3 minutes.
We'll do it tomorrow. All right. Have a great day.